Okay, hello. This week's video is on the subject of lambdas in C++. It's another one of the Inside the Black Box videos. So the idea is we're going to be showing you what lambdas are, what they do, and how they work. Now, I will sound a note of warning on this, as I'll show as I go through it. Lambdas actually genuinely do things that you cannot directly replicate yourself. They are very useful, but they are one of the bits of C++ that has to be implemented by the compiler actually doing something special. They don't just implement a lambda in C++ and you're using effectively a built-in library of the compiler. They really do require the compiler to do something special. But nonetheless, by having a look at how they work behind the scenes, you can get a much better feel for what they're doing and what their limitations are, and equally what their strengths are. So first of all, I'll just go through and show a lambda in action. It's something a lot of C++ programmers have seen, but by no means all of them, because they are useful for specific jobs, but only specific jobs. So I, for once, do not have to include any headers except for my IOStream header, because lambdas don't use anything header-wise, because, as I say, this is something built in large part to the compiler. So I'll create my main function, and I will just create a lambda, okay? And I will briefly talk through the parts that make up a lambda, just in case you're not familiar with them. But you'll see kind of what they are as I go. So this is a very simple thing. And I'll finish this program, which is then I will do something like lam 1 2 3 4, and I will compile that. And I missed a semicolon on the end of that line. That's very easy to do with working with these lambdas, because they do look a bit weird. Okay, but when I compile it, what effectively happens is the thing that I typed in here when defining my lambda, this bit, is executed as code. And this is basically what lambdas are. They are anonymous functions that you define inside other code. Now, this is an idea that a lot of languages have. C++ has its lambdas. Functional programming languages almost all have things like these, where they're usually called closures. Closures and lambdas are different and important technical ways, but we'll gloss over that entirely here and just say that's something. And there's even something a bit like it, which is now deprecated and considered bad form to use in Fortran, called function statements. So the idea of defining functions inline in your code is one that goes back a long way. That's not some modern Fortran feature they've decided they're taking out. That's a very old feature. So as I said, I will describe what all the bits of this lambda are. So the obvious bit is here is the code. This is the definition of your function. It's inside curly brackets like any other function you define. This here is the parameter list to the function, the signature of the function, if you will. It tells you what the parameters to it are. And this here is where things get a bit clever. It's called the capture section. Now, because I'm going to be explaining how lambdas work, I need to go through this in a little bit of detail. So the idea of the capture section is that it allows you to take information from the containing scope where you create the lambda and contain it inside the lambda where it can be retrieved and used in the lambda. So for example, I can create here another integer, j, which I will give the number 900 to. And if I capture j here in this capture section, I can not only output I, but I can output j there. And that works. It's acquired that number 900. Now, that doesn't look too remarkable. If I take this j out of the capture section here, this won't work. It doesn't know what j is, but you would think on some level that, well, that's just a scope issue. But it isn't, because lambdas actually copy and take the values with them as they go, unless you tell them not to. So if I create a quick demo function here, I'm going to call retlam, and I'm going to pass in a fixed number as a parameter to it, and I'm then going to return a lambda that captures that fixed value, takes the other integer, and then I'm just going to copy the rest of the body here, because what it actually does isn't very interesting here, but that's no longer j, that is now fixed. And I can now get rid of all of this. I can have my lam here is retlam of 1, 2, 3, 4, 5, 6, say, and I can compile that, and it runs, and it has captured this value. So this fixed note here, it's being passed as a parameter of this retlam function, so it's a stack value. As soon as you exit this function, this value goes away. It doesn't exist anymore. So what is actually happening here in this capture section is you are taking a copy of the value. Now, it is possible to do capture by reference in these things as well, but we're going to ignore that here for the purposes of not going completely mad while describing them. But essentially, the idea is what this lambda is doing is it is able to capture some or all, you can tell it to capture everything, of the variables in the place where it's defined, and keep them with the lambda wherever the lambda goes. And now this is the other thing that will strike you if you've seen things like this before and you see what I've done here. So this function returns just a variable. This auto here means that it infers the type of the variable from this return statement, and I'll say why that's important in a bit. But what I'm doing is I am returning this lambda, and what I'm getting back is an object. So this is essentially C++ treating a function like Python does, as a first-class object. This is a separate thing. A lambda is not like a normal function you can just have a function pointer to, but it's always the same function. If I call retlam twice with two different values, so if I put in here auto lam2 is retlam minus 1, 2, 3, 4, and then I call lam2 1, 2, 3, 4 here, and compile that, you can see this capture has captured the different values and it's still got them. So clearly these things are something a bit more sophisticated than just being a function behind the scenes. So just before I go into saying what they, well, not exactly what they are, because as I say, these are something that the compiler has to implement at the core, I believe anyway, I will just note one other point here. So all the way through here, in the return value from this function and in these variables here, I have used this auto keyword. Now auto is a keyword that hopefully every C++ programmer nowadays knows about because it's very useful. It means infer the type of this variable from the way that it is defined. So when you define a variable, when you assign a value to it for the first time, this auto means infer the type of this. And mostly it's just a convenience feature. It means you don't have to worry about what the type is. So, you know, for example, in particular, it's extremely useful when you are getting iterators over containers, because remembering that it's, you know, standard array iterator just makes your life that bit harder. Auto makes it easy for you. But here, in the case of lambdas, it's not just a convenience. The C++ standard does not require lambdas to have any particular form at all. So as a consequence, officially, everyone's consensus is if you want to store one of these lambdas, you only have two options, or three. One is to use these auto variables in order to infer the type automatically like this. Two is to use the templating system and template on the type of your lambda, because that works as well. The compiler knows what type it is, but you don't. And in particular, if you want to pass a lambda to a function, you have to use either a template or the thing I'm going to mention next, which is the standard function. Now, standard function is probably going to be something that we talk about in a future inside the black box video, because it's quite interesting how it works. But essentially, it's a way of allowing you to store anything that implements round brackets. And that sort of gives you some of the trick for how all this actually works. Because you can implement the round bracket operator on any class that you want. So let me just define a class that I'm going to call demo for simplicity. And everything about it is public. I've just made it a struct, but never mind. And I am going to have inside it an int, which is stored, and it is going to have a function which is operator round brackets. It takes an integer and has as its payload, once again, all of that. And now I'm going to change my retlam, and I must read in here, just to make this easier, create a constructor for this, which is going to take that integer, and it's going to set stored is store, so that you can create one of these and store a value with it. So I can now get rid of my lambda here. And I'm not going to do that. I'm instead going to return a demo capturing the value of fixed. And that should compile. Yes, I forgot to change a payload in that operator. That's what I did. So that should not be fixed anymore. It should be stored, because I've captured it under another name. And there we go. That runs exactly the same. And you can see now it'll have pretty much the same properties that the lambda does. So I've been able to take a value and store it inside my class. I've implemented the round bracket operators, so I can call it like a function. And I can happily, return a value like this, because it's a simple class, so it's copy constructible. Even if it was a more complicated class, you could still define a copy constructor for one of these. And that sort of explains at least one of the ways in which these lambdas work. They really do, quite often, as far as I understand it, in implementations, effectively create behind the scenes one of these classes that implement the round bracket operators. Because of the fact that the compiler is able to know a lot more about the behavior of lambdas and things, it's able to do optimizations it couldn't do on these classes. And the capture section allows you to do things you couldn't easily do with this. In particular, it's possible in the capture section of a lambda, that bit in the square brackets, to say capture all variables, or capture all variables by reference. And you couldn't, in general, do that yourself, because a compiler doesn't really have a concept of doing that. It probably is possible to do some of the other lambda-ish tricks using the templating system, but I think that one is why lambdas have to be implemented as a core compiler element. It's not part of the standard library in the sense of being implemented in C++. And that basically shows pretty much everything about lambdas and how they work. Now, once again, the point of this is not because I think doing this thing with these classes implementing round bracket operators is superior to a lambda. It isn't. In almost every possible way, if you can use a lambda, you should use a lambda. The compiler is able to optimize them further. They have a fairly readable syntax. They have the huge advantage that you don't have to create one for each possible capture. I created a class here that captures one integer because that's what I showed you before with the lambda, but I'd have to create a completely different class if I wanted to store one integer and one float, say, whereas the lambda syntax would be very nearly identical. So they have huge advantages over creating these, what are often called, slightly inaccurately, functor classes. But it is worth knowing that these things exist, that you really can create your own classes that implement round bracket operators. And I will add that standard function that I mentioned can store your own custom written classes so long as they implement this round brackets operator. That's one of the great powers of standard function that, as I said, we'll probably come back to at some point and explain how that works. But it is very useful to know that what a lambda does is not completely magic that you can't understand. It is creating an object, an instance of an object that has those bound parameters to them, and it does then effectively implement round bracket operators on top of it. The fact that you have to use this auto when working with lambdas, or one of the other things that I mentioned, suggests that it's not as simple as this is absolutely definitely the way everyone will be doing it. The standards committee clearly didn't feel there was any reason to define a specific way of doing it so that you could have a syntax for this is how you store one of these when you've got one. That's something that's left up to the individual compiler writers. But it is, as I say, useful to know that there is, once again, no magic here. You open up the black box and you see something that to a very great degree you can, admittedly, with lower optimization levels from the compiler and a much less convenient way of doing it, you can do it all yourself. And there really are very good reasons for wanting to write classes that have these round bracket operators defined on them, all of your own. But that may well also be a topic for a future video. So I will finish this one now and we will be back next week.